Good afternoon, students. Myself, Shiv Shankar, Associate Professor, President's University, Bangalore. Today, we are going to discuss about Meissner Effect. This Meissner Effect is a very important phenomena which is exhibited by the superconductors. That is, the magnetic flux expulsion by the superconductor when the superconductor is cooled below the critical temperature. This phenomena is known as Meissner Effect. You can see here, a superconductor is in a normal state. That is, when the temperature is greater than the critical temperature, the superconductor is in a normal state and all the field lines are penetrating, passing through the body of the superconductor. But the same superconductor, when it is cooled below the critical temperature, the superconductor goes to the superconducting state and all the magnetic flux, all the flux is expelled out of the superconductor. And it is said the superconductors are behaving like a perfect diamagnet. That is, the susceptibility of the superconductor is -1. Now let's understand how this susceptibility is going to be -1. Now recollecting the magnetic flux equation, in terms of magnetization and magnetizing force, that is, during magnetization, the magnetic flux equation can be written as B is equal to mu naught times M plus H. M plus H. Here B is said to be magnetic flux density and mu naught is magnetic permeability and M is the magnetization and H is the magnetizing force. Now let's see, we all know that each material responds differently when you apply a external magnetic field. Some develop a strong alignment, strong magnetization. Some develop a weak magnetization. I mean, strong alignment is seen in case of ferromagnetic material, and a weak alignment is seen in case of paramagnetic material, and a very weak magnetization occurs in a diamagnetic material, but in the opposite direction. So during this magnetization process, this is the equation which follows. Now you can see that here what is happening. You can see during superconducting state that when temperature is less than the critical temperature, and we all know that the superconductor is in a superconducting state. The superconductor is in a superconducting state, and you know that in that case the magnetic flux density becomes 0. Now substituting these values in the above equation, what we get is 0 is equal to mu naught into M plus H. Now rewriting this equation again, you get mu naught into M plus H is equal to 0. And what you get is M plus H equal to 0. Because mu naught is a magnetic permeability and it will always have some constant value. And you all know that mu naught is equal to 4 pi into 10 raised to minus 7 Tesla meter per ampere. Now that is the magnetic permeability in a vacuum. Now what you get here is you are getting M plus H equal to 0 and M is equal to minus H. Now what is important is the magnetization developed in a superconductor is minus times the applied magnetic force. That means the magnetization in a superconductor is always such that it is equal to the magnetizing force, applied magnetizing force, but in the opposite direction. That means it is trying to cancel out all the applied external magnetic field. Now we all of us know the magnetic susceptibility is given by M, magnetization developed in a material, divided by the force applied. And you can see here what you get is m by h, what we are getting here is m by h is equal to -1, and therefore chi is equal to m by h, which is also -1. So chi is -1 here. So chi is -1 here, which suggests that the superconductor during superconducting state behaves as a perfect diamagnet. That is, there is a complete repulsion of the magnetic flux lines by the superconductor. Okay, friends. Happy learning. Wait for my next lecture.